Wouldn't it be brilliant to implement all motion control applications directly with SIMATIC? This would mean setting up the communication with drives and programming the command coordination and synchronization of access directly using Step 7 in the TIA portal. Now this dream is a reality. The S7-1500 CPU is a modern motion control system. Thanks in particular to the S7-1500 technology CPU and the integrated CAM disk functionality, we can very conveniently implement simple and complex access couplings. I'd now like to introduce this CAM disk functionality in greater detail. Let's take a closer look at the setup. To do this, I'll first switch on both axes. We can see two motors, each driven by a Synamics V90 servo drive. And the higher-level S7-1500 technology CPU actuates the drives, providing the movement commands and coordinating and synchronizing both axes. The right axis moves continuously, and the left moves in relation to the right axis, sometimes to the right, sometimes to the left, then back to the right, and so on. This is coordinated by the SIMATIC. What could be behind an application like this? Let's take a look at an animation. Here we see two movements. The press, which is driven by means of this continuous movement, and the material infeed, which moves the material forward at the right time and at the right position of the press. This positioning relationship can be shown in the diagram, as we see here at the top. For each position of the press here on the x-axis, we see the position of the infeed, which moves forward and back accordingly. Now we want to create and configure this mathematical CAM disk here at the top in the TIA portal. To do so, we switch over to the TIA portal project. Here in our project, we've already inserted our two Synamics V90 converters and the S7-1500 technology CPU. In the CPU, we can already see two axes, the axis for the press and the axis for the feed. Both axes are actuated in the program, specifically by means of the system functions that provide the requirements for the traversing movements. In order to switch on the axis, for example, or to start and stop the press. Now we want to create a CAM disk in order to define the positional relationship between the press and the gripper feed. To do this, we create a technology object CAM. In the CAM disk editor now appearing, we can very easily define and optimize the CAM disk in various ways. Here we can see the x-axis, which represents the position of the master axis, in our case, the press. The y-axis of the diagram indicates the slave axis, in our case, the infeed. We'll now adapt the scaling in order to adjust it according to the units we'll be using. The press moves between 0 and 360 degrees. That's fine. We'll define the infeed so that it moves from the left side from 0 to the right side to 40. To more accurately create the CAM disk, we'll add a grid with the spacing set to 1. By doing this step, all the preparations for the creation of the CAM disk have been made. Now we want to specify at what position of the press the infeed is located on the left and when it is located on the right. In other words, when the infeed is at 0 and when it is at 40. We can either specify this graphically or use the table here at the bottom. We'll choose to do it graphically, and we defined the position of the slave axis for each position of the master axis, the press. If the press moves between 0 and 40 degrees, the infeed continues to stay at 0. If the press moves between 0 and 40, the infeed continues to stay at 0. If the press now moves farther, the infeed should then move forward. And if the press has arrived at 130 degrees, the infeed should stop at its right-hand position during the press cycle. That is, until the press has arrived at 230 degrees. Afterwards, the infeed should return again. And while the press is turning 270 degrees and 360 degrees, the infeed should stop on the left-hand side. We have now defined our ranges, when the infeed is on the left, when it's on the right, and when it's once again on the left. We see this graphically and also in the table here at the bottom. Between the ranges we've defined, the system has automatically filled the gaps. That is, interpolated the gaps and inserted the transitional movement. In addition to the pure positional relationship, we're also interested in the speed, the acceleration, and the jerk of the slave axis. We can also have this displayed by inserting an additional figure. And now we see the speed, the acceleration, and also the jerk of the slave axis, that is, of the infeed. Here we see, however, that with this type of interpolation, there are jumps in the acceleration. Everything is displayed to us here at the top with this warning. The system tells us that we don't have a smooth traversing movement. Of course, this can be optimized by adjusting the transitional movements. To do this, we open the characteristics and switch over to the VDI-based optimization, where we can now precisely define the acceleration, the speed, and the jerk for this traversing movement, along with the type of interpolation. From this setting alone, we can already see that the jump in the acceleration has disappeared, resulting in a smoothly changing speed emerging here, and overall a very smooth traversing movement. We apply the same method for the second transition. We switch over to VDI-based optimization, and we now can see a smooth traversing movement. With these steps, we've created our cam disk, that is, our positional relationship between the press and the infeed. Now we actually want to use this in order to couple both axes. We go into our user program and add the function in our next network in order to couple the infeed. We use the functions in order to first prepare the cam disk. Before the first use of the cam disk, it needs to be interpolated, that is, calculated by the system and made available. This means that if the infeed is to be coupled, the cam disk is interpolated. As soon as it has been acknowledged with done, we proceed to the actual coupling using the function CAMIN, and we couple the infeed axis to the press axis. This means simply dragging the press here as the master axis, the infeed as the slave axis, and both axes are to move in a coupled manner through the positional relationship we've just defined. The whole procedure should be launched as soon as the cam disk here at the top is available. There are also options to adopt, move, and scale the cam disk. For example, on cam disk pitch to 1, which is naturally also an option. In our case, however, we're sticking to the basic settings. The question still arises, how do we perform the coupling? This is performed either by specifying the path or by specifying the dynamics. We choose to specify the dynamics, and we select 0, but we leave the default settings of the dynamics as they are here. As a final step, we can also specify whether the cam disk should pass through once or cyclically. This means when it is at the end, it restarts from the beginning, and that's what we want to do here. We've now coupled the infeed to the press via the cam disk we just defined. In order to stop the infeed axis again, that means to uncouple the infeed. We need to add positioning command to halt the infeed at 0, and therewith stop and uncouple it. That's it. We've managed to couple both axes that quickly. Let's once again review the final result here on the configuration. We see the right axis moving continuously, and the left axis is coupled by the somatic via the cam disk. As you can see, we quickly created the cam disk, defined the position ratio, even optimized the cam disk, and coupled both axes to one another in the program. Now that's integrated engineering in the TIA portal with the Cynamic S7 1500 technology CPU.